this lecture, we want to continue our earlier theme about the yarn unevenness. On the end of last lecture, we said something about the Hubertus index of irregularity, and we came to the conclusion that something is wrong in Martindale's concept of sliver or yarn irregularity. The question is why? The question is why? Because exists something so, some authors or institutions make some empirical corrections. For example, so-called Uster, precisely company Zellweger in the Switzerland, in a town named Uster. But it is known as a Uster Instruments and Uster Company. They use for coefficient of variation of local sliver fineness. When I speak about the sliver, it's a little theoretical. Practically, we use it at most for the yarn. Yarn is also something like some sliver from fibers. They used such formula because logarithm of this is straight lines, and you know the graphs from Uster which have the trend to be straight lines at most. Interesting work is dated 1964 from author named Bornet, which formulate the idea why the real yarn irregularity is higher than the calculated value based on Martindale's concept. He is meaning that it is because fibers are not individual, then in some bundles or similar aggregates. Nevertheless, it's verbal. Nevertheless, then he used quite empirical equation, which is this here. We accept generally the idea of Bornet that the influence, the center of influence is in some fiber aggregates, and in opposite to him, we derived a model exactly. So let's think at first step about the Martindale's assumptions. Martindale used the assumption fibers are straight and parallel. Okay, it's idealized. We can say that yes, as idealized maybe. He assumed fibers have same length. We can say also idealized, yeah, but why not? Maybe. Fibers are positioned randomly along the sliver. It's evident, yeah, yes. But he assumed also and individually. And this is not right. We have enough experimental results too, generally in the world, that the fibers are not perfectly one beside the other, but they are moving together in some fiber aggregates. Therefore, we created following model based on the idea which is shown on our picture. The basic structural unit is a fiber, this here. From fibers is formed a bundle. A bundle, it is an aggregation of several fibers which are together or glued or knots, yeah, so that the separation of fibers into individual ones is not possible by technological process used. Yeah? So they functioned as a, for example, couple of such fibers functioned as one thick fiber. This is the bundle. From bundles are created clusters. Cluster is formed from aggregation of several bundles. The clusters are only loosely bonded together, and these could be sometimes separated by applying suitable technology. Bundle is to infinity for us. We have the fibers together. Cluster is possible sometimes based on the local relations in technological process, divide us to smaller clusters or no, based on the situation what we do in spinning mill, for example. This is the cluster, and then the sliver or yarn finally is formed from aggregation of several bundles, so that from these units we obtain the final structure, sliver. The lower units create the higher unit randomly, and the creation are mutually independent. They are our assumptions. Please, it is a little difficult in short time to have all in head, because it's not practical possible to each quantity a subscript write fiber, bundle, cluster, sliver. Then we use numbers. Which is related to fiber, it's 4, number 4. Which is related to hard bonded bundles is number 3. Which related to clusters have number 2, and which is related to the yarn or sliver have the number 1. Yeah? So 1 is yarn, 2 is cluster, 3 is bundle, and 4 is fiber. Yes? Okay. We imagine that we create from fibers, number 4, bundles, number 3, then from bundles we create clusters, number 2, and then from clusters we create sliver or yarn cross-section, number 1. Yeah? In reality it's in opposite. We have some material, and this material we divide to clusters, bundles, individual fibers, and so on. Yeah? But let's imagine this structure. This is our idea. Now the quantities. Number of the smaller parts in higher unit. So that a number of clusters in sliver cross-section we call Q21. 2 is cluster, 1 is yarn or sliver. How many clusters in the moment is in yarn or sliver cross-section? Number of bundles in the sliver, it's Q31. Number of bundles in yarn sliver. And number of fibers in yarn cross-section or sliver cross-section, it is Q41. Fiber, yarn. Yeah? Our old symbol was a number of fibers in yarn or sliver cross-section. Number of bundles, what is it? Number of clusters in cluster, evidently 1. How many clusters is in a given cluster? 1. Number of number of bundles in cluster, it's Q32. Bundles in cluster, bundles 3, cluster 2, yeah? it will be necessary to use this system of subscripts, and so on and so on. This is the numbers of smaller parts in higher unit. Evidently, it is valid equations for mean numbers. For example, here, mean number of fibers in cluster, it's mean number of fibers in bundle times mean number of bundles in cluster. Based on such logic, all these equations must be valid. The same is maximum numbers, similar equations. Maximum number of fibers in cluster, it is maximum number of fibers in bundle times maximum number of bundles in cluster. Yeah, it's logic. On this logic, all these equations are constructed. It's evident that it is valid. Now to fineness. Sliver fineness we call in the moment T1. Our older symbol was capital T. Yeah? So T1 is same than earlier capital T. Coefficient of variation of sliver local fineness is V1. Why 1? Because structure number 1, sliver. Earlier it was V capital T. Yeah? Cluster. Fineness of the cluster is T2. Coefficient of variation of this is V2. Coefficient of variation of fineness of clusters. A bundle. Fineness, the moment fineness of a bundle, some bundle is T2. Coefficient of variation of finances of from all bundles is V3. And finally, fiber. Fiber fineness is T4. Fiber have subscript 4. It was identical as earlier small t. And coefficient of variation of fiber fineness is V4, identical of earlier symbol Vt. What we can write now? Fineness of the sliver or yarn is 0 if number of bundles, number of clusters in the yarn is equal to 0. No 1 there. And fineness of sliver is sum of fineness of all bundles in clusters in all cross section from first to last. So that it is this here. But what is T2? This fineness of cluster. It's equal to 0 if no fiber is there, if number of bundles is 0, and similarly sum of all fineness of bundles over all bundles which are in the moment in cluster. This here. The same, what is the fineness of bundle when from fibers? It's 0 if no fiber, and it is sum of fineness of fibers over all fibers in bundle. Yeah? Let's see these three structures, this, and this. All these three quantities, T1, T2, T3, are random quantities. Type Y. We made in last lecture some small excursion to theory of probability. We define some random quantity type Y, and we postulate how it is with coefficient of variation of such random quantity. All the three All the three are quantities type Y. So let's imagine now that each quantity T1, T2, T3 have is a random quantity and have the binomial distribution. No, identical, but all three are type binomial distribution. Therefore, in short here, 3 times binomial distribution. We defined such equation. Using this type of expression, what is this? It's mean number by maximum number. And this is divided by maximum number. Now, for a V1 square, based on this formula, for V1 square, we obtain this equation. Mean value, maximum value. For V2 square, we obtain such equation, similarly. And from V3 square, we obtain this equation. The way how to obtain it, I think, clear. Yes. So what is V1 square? V1 square. It is this here, but on the place of V2 square, I can use this expression. So it is, what is it? By Q bar to 1, and here is plus this brackets, yeah, here, plus, and on the place of V2 square, I use this expression. So it is this here, it's by Q bar 3, 2, and so on, samely. But here is V3 square, and other place of V3 square, I can use this expression. It is here. So, coefficient of variation of sliver, V1 square of it, it's given by this expression. After rearranging, we obtain this here. After rearranging. And using equations postulated earlier, we obtain, because for this Q bar 4 3 times Q bar 3 2 times Q bar 2 1 is Q bar 4 1. It is written earlier. Where it is, for example, here it is. In some expression it is here, yeah. So, so that we obtain this expression for sliver local coefficient of variation. And now let's accept two ideas. The first is when you produce a ring span yarn, for example, then the drafting system on the ring frame can work with a coarser sliver or finer sliver based on count of final yarn. A relatively higher number of fibers will be passing through the drafting system together as a cluster respectively when we produce coarser yarn from a little coarser sliver, because more fibers in the drafting part of ring span ring frame. When in another process, rotor spinning, a relatively higher number of fibers will be transported per unit tooth of opening roller when we produce coarser yarn or we use coarser sliver. So that when we produce yarn having more fibers in cross section, maybe the number of clusters which are created, our yarn, is higher, and vice versa. So, therefore, we can postulate or say some assumption, of course it's some simplification, that number of fibers, mean number of fibers in one cluster is proportional to the number of fibers in yarn cross section. When we produce coarse yarn, the number of fibers is in yarn cross section is high, and therefore also the clusters which are created this yarn will be bigger. So that we can write Q for 2 bar is P times Q for 1 bar in our addiction, where the parameter P is a parameter of proportionality, and it has some sense. It is a measure of fiber individualization. It means if P is small, then number of fibers in our yarn is created from clusters having small number of fibers. Yeah? If P is high, then vice versa, our clusters will have lot of fibers. Things about this phenomenon, we will use this equation in our equation for V1 square. In the same time, now we come back to our traditional symbols as possible, so that on the place V1 we give back Vt, on the place V4 V small t, on the place Q bar for one number of fibers in mean number of fibers in yarn or sliver cross section small n bar, it's T by T and so on. Using this substitution plus this assumption, we obtain such equation, and symbolically we can write that this part have the name A, capital A, and this whole part, yeah, we'll name a capital A, and this part P times this here, it is called the symbol B. When A is this here and B is this here, we obtain coefficient of variation in this form as and if n bar is T by T, T bar by T bar, we obtain the final equation in such form. It's a difference between in relation to Martindale's equations, because we are here the part B which is multiplicated by number of fibers. Generally say it is also theoretically possible in this moment that 1 plus V square T can be smaller than, can be higher than our part A. Theoretically can be. So that theoretically we can also to obtain the unevenness or irregularity, unirregularity smaller than limit value based on binomial sliver. It's only theoretical example, in the practice nobody watch it, but theoretically it is possible. More easier it is when we use, for us easier, distribution, when on the place of binomial we give the Poisson distribution. We derived it by Martindale's concept. What is Poisson? What is in the Poisson distributions? Also 3 times, of course, distribution of fineness of bundles, clusters, and yarn. But type for each 3 Poisson distribution. then in Poisson distribution the maximum number of possible cases is limited to infinity, isn't it? So that by Poisson, in Poisson version, Q43 max as well as Q32 max as well as Q21 max is limited to infinity. Then our part A, using this limit, have this form. You have this form. And our part B, after this limiting, is equal to P, the parameter which say us something about the, I mentioned it where, measure of fiber individualization, isn't it? So, and formally the final equations, they be same, have the same shape. By the way, what is more in relation to Martindale? Martindale have here 1 plus v squared t. Now we have here plus q bar 43. Number of fibers in bundle. It means in a structure in which the fibers are fixed together, glued, knotted, so that it is not possible through our technological process it divide. Yes. How is the practical result? It is an older experiment because earlier it's better for us than today's, the last versions from USTA statistics. Why? In the modern spinning process, the draw frames are used with some mechanism of regulation. They can very intensively regulate the irregularity or regulate the unevenness of sliver. Therefore, also the yarn have smaller value. We studied this yarn unevenness as a pure random process with some special regulations, yeah, of this one. Therefore, I use the result as an example, a result from USTA Statistics 1997. The best is maybe the graphical explanation. On the abscissa here is mean yarn count. It is for yarn, carded cotton yarn. Yarn count in text. This is here. On the ordinate is coefficient of variation according coefficient of variation of local yarn fineness, yarn count. The USTA results are the thin lines here. You know these USTA graphs. But now it is not linear because I have linear the abscissa scale. The scale on the abscissa is here linear. In a standard USTA graphs, this abscissa is this graph is semi-logarithmic. Therefore, in semi-logarithmic graph or a logarithmic graph, you obtain a linear relation graphically. This is without logarithm. Therefore, the USTA result is the thin lines here. And because you know in USTA graphical interpretation they use a little thick red lines, I showed also in dotted lines how is the thickness of this red line in the pictures from Zellweger USTA. Yes. Using our equations and having two parameters A and B, suitable parameters, we obtain thick curves here, set of thick curves here. You can see that in practical used region, our curves are lying practically inside of thickness of Uster red line. Yeah? So our model can very good to approximate, or no, approximate, to interpret better the experimental results published by Uster. Yes. Therefore, because this influence, because these bundles and so on, the real unevenness is higher than the ideal unevenness according Martindale. Here are some for curve 50%, Uster curve 50%. Some graph which show how it is in different types of yarns. Here is Q for 3 as a function of which is a minus 1 minus v squared t, and Q bar for t, it's a how is the number of fibers, mean value of number of fibers in the fiber bundle. Yeah. Don't worry that it is starting from 0. We speak about the Poisson distribution. So Poisson is in Poisson distribution also number equals 0 is possible, as well as in binomial distribution. Only in real yarn, when we have some part of yarn in which number of fibers is 0, then it is braked. There is some knot here. Yeah. Therefore, it is going from 0 in a special, in a cited, where it is, in a cited publication in Melian Textilberichte. Here it is, yeah. Here is cited a publication in which it is written in more details. It is shown how it is with non-braked yarn. But what is interesting, from this dotted line right, theoretically it's possible to apply Poisson model, Poisson's distribution. On this line on the left is not possible. It must be used binomial distribution. So you can see that to say that the Poisson distribution can be used for each yarn is not well. We can formally use it, but we don't obtain in relation to the model right results. Yeah. You can also see that the parameter B and A are differed in different type of yarns. When we will longer time watch this diagram, you can see that it's, for example, interesting differences between ring yarn and rotor yarn. In rotor yarn, the cluster, the number of fibers in cluster are relatively small, as shown this experimental experiences, and the values here are relatively small, smaller than in ring yarn. Nevertheless, the bundles, this smaller number of fibers in the bundle is higher. Please don't imagine number of fibers in non-destructible bundle is not too high value. It can be 1.7 for rotor yarn, for example, or 1.3 or 1.2 mean number of fibers. It means sometimes one fiber, sometimes two fibers together, sometimes 3 fibers together, and 4 fibers together is a chance as in lottery. Yeah? Imagine so, but it can play significant role for a yarn unevenness. Yeah? In a rotor yarn, the cluster, the cluster is from a small quantity of bundles, but the bundles are a little thicker. For example, 1.8 fibers, mean value of fibers, in opposition to ring frame, on which we obtain 1.1, for example, 1.2, something so. Yeah. It is in a ring yarn. It is vice versa. In ring yarn, because drafting process make the fine sliver, which is twisted then, because drafting process, the clusters have the tendency have more bundles, but in bundle is only a little more than one fiber. Yeah, for example, 1.1, 1.2, based on our experimental experiment. So that you can see that we can also divide. We can also divide the two influences. One influence is the fibers are based on our technological principle permanently together, glued, knotted bundles, and the second is the clusters, which can be, when our process is good, can be divided. And it brings us, when we analyzed our data from industry, based on this, it's theoretically it is very easy, because this equation, where is this equation? It's a it's a linear equation, or you can use the linearized statistical regression, and from set of data, I don't know, for last half year, from your spinning mill, to obtain the parameters A and B for your yarn. It's evident. And now, when A is too, now you have some yarn which is not good, the irregularity is too high. Based on this analysis, and you can compare your data from last half year with, I don't know, the data which are here, for example, from USTA and so on. When A is too high, when A, the quantity A is in your yarns too high, what it means? A is, in the case of Poisson distribution, 1 plus V squared, it is the same by Martindale, but plus Q bar for 3, number of fibers in our bundles. When you have too much fibers in bundles, non-destructible bundles, what you can do? You can cry only. You can cry, and you can find on the market another type of material which have not so intensive tendency to create such bundles, because this is the influence of the material. When you have bad value of your yarn unevenness, and based on this analysis, you obtain to them that B is false. B is, in Poisson's model, equivalent to P. Then, no, false, sorry, that P is too high. It means you have too big, not these bundles, than the clusters. Yeah, our clusters. You have too big the clusters. Then what can you do because to obtain better unevenness? Big fight in your spinning mill. All people must watch. Why must rearrange machines in the carding machines? The surface of this whole cylinders must be sharp. All this arranging of machine must be optimum, and so on and so on and so on. You can start to make some big fight in your spinning mill. Yeah. In the first case, no. In the first case, you can only cry and or find on the market another type of your, I don't know, cotton fibers, which have no so high tendency have the fibers together. In the second case, you must organize something like big fight in your spinning mill. And there's the practical end for our theoretical model. Principally, we use the same idea than Martindale. Nevertheless, we apply it to a more general idea, now from individual fibers immediately yarn. From individual fibers we create bundles, from bundles clusters, and then from clusters the yarn. This is the difference, logical difference to Martindale. You can say how we obtain this system. It was developed, and my first version of model was only in 3 steps: from fibers to clusters, and from clusters to yarn. But when I compare it with our own experimental research as well as the USTA diagrams, especially for this fine part of the yarn, this curve wasn't enough precise, wasn't enough well. I think what is the logical sense of this no good results in one part of the curves? And we came to them that logically it must exist something like these bundles, some fiber bundles which are based on our principle used, technological principle used, are permanently together, no possible to divide it. Yeah, and then finish our lecture.